Welcome to our deep dive into abstraction logic. You've sent over some excerpts from Stephen Obua's book, Abstraction Logic.
Okay.
And let me tell you, this stuff is fascinating.
Yeah.
It's like he's taking the worlds of math and logic and kind of smashing them together to create something entirely new.
Right.
Plus, the book's still a work in progress, so who knows what other mind-blowing ideas are yet to come.
It's definitely ambitious. Obu's goal is to redefine the foundations of math and logic. And from what I've seen,
Hmm.
he's aiming for a system that's both incredibly simple and remarkably powerful.
I'm intrigued, but where do we even begin?
Yeah.
My notes mention something called a mathematical universe,
Okay.
which sounds pretty grand.
That's the starting point.
Okay.
Imagine a container labeled U holding all the mathematical objects we're interested in.
Okay.
We call this U the mathematical universe.
So we're talking numbers, sets, functions, the whole shebang.
Exactly. But here's the cool part. U isn't fixed.
Okay.
It's like a tailor-made toolbox.
Okay, big.
For a simple problem, you might only need a few basic tools like the numbers 0 and 1.
Okay.
But for something more complex, you can expand your universe to include a wider range of objects.
So it's about choosing the right tools for the job,
Yeah,
just like a carpenter wouldn't use a hammer to saw wood.
that's a great analogy.
Okay.
Now, once you've defined your universe, you need ways to manipulate those objects to actually do something with them.
Right.
That's where operations come in.
Okay, so like adding, subtracting, multiplying,
Mm-hmm.
the basic math operations we all learned in school.
Those are perfect examples. Operations take values from your universe and combine them to create new ones.
Okay.
Abua illustrates this with a simple calculator.
Okay.
It has a universe of numbers,
Mm-hmm.
but to be useful, it needs operations like addition, subtraction, multiplication, and even division.
But what about dividing by 0? That's a recipe for disaster.
Exactly. That's why even a simple calculator universe needs the concept of error.
Okay.
Otherwise, it wouldn't be a very reliable tool.
I see. So we're already starting to think about the limitations and potential pitfalls of our mathematical universe.
Precisely. And it gets even more interesting when we move beyond basic arithmetic.
Uh-huh.
Obua introduces operations like summation and product, which work on sequences of numbers.
Mm-hmm.
He even has this eater operator, which is like a super-powered version of summation and product combined.
Oh, my brain's starting to stretch a bit here, but I'm loving the challenge.
Good.
So we've got our universe of objects and a bunch of operations to play with. What happens next?
This is where things get really mind-bending.
Okay.
Obua brings in Cantor's theorem, which essentially says there are always more operations than objects.
Okay.
Even if you have an infinite number of objects.
Wait, more operations than objects. How is that even possible?
It's a bit counterintuitive, I know.
Yeah.
But think about it this way. Even with just the numbers 0 and 1, you can create an endless number of operations.
Mm-hmm.
You could have an operation that adds them, one that subtracts them, one that multiplies them, one that raises one to the power of the other, and so on. The possibilities are literally infinite.
Wow. That's pretty profound.
Yeah.
So no matter how big our universe gets,
Right.
we'll always be limited by the sheer number of ways we can manipulate those objects.
Exactly. And this leads to a crucial question. Where do we put all these operations?
Right.
We can't just cram them into our universe U alongside the objects,
Yeah.
or we'd run into all sorts of logical paradoxes.
So we need a separate space for operations.
Yes.
But then how do we actually use them?
That's where Abua introduces the brilliant concept of operators.
Okay.
Think of them as functions that act on operations,
Okay.
not just on the objects themselves.
So operators are like a meta level above operations.
Yeah,
They're the puppet masters pulling the strings.
that's a great way to put it.
Okay.
One example he uses is the length operator.
Okay.
Imagine you have a universe array containing all possible lists. The length operator acts on an operation that creates a list, giving you the number of items in that list as a result.
Okay. I think I'm starting to see the beauty of this system.
Yeah.
We avoid contradictions by keeping operations separate and then use operators to manage and apply them to our universe of objects.
Exactly. And this leads to a whole new way of thinking about algebra, which Obria calls abstraction algebra.
Okay, I'm all ears.
Yeah.
How does abstraction algebra differ from the algebra I struggled with in high school?
Remember how in traditional abstract algebra you have a set of objects and a set of operations defined on those objects?
Vaguely.
Mm-hmm.
Like the set of integers with addition and multiplication.
Perfect. Abstraction algebra takes it a step further.
Okay.
Instead of just operations, it focuses on operators.
Okay.
So you still have your universe of objects,
Mm-hmm.
but now you have a collection of operators that work on the operations within that universe.
I'm trying to picture this. Can you give me a concrete example?
Think back to that calculator example. We started with basic arithmetic operations, then added summation and product.
Yeah.
Each time we added more operators, we essentially created a new abstraction algebra, a new level of complexity.
So it's like building a skyscraper, adding more and more powerful tools to manipulate our universe of objects.
Exactly. But why call it abstraction algebra and not operator algebra?
Right.
Obua explains that operator algebra already has a specific meaning in another area of math.
Okay.
Plus, he's interested in the bigger picture, how different abstraction algebras relate to each other.
Okay.
He calls this common structure a signature.
So the abstraction part emphasizes the shared structure between different algebras.
Precisely.
Okay.
It's about identifying the underlying patterns and relationships, the blueprint that connects them all.
Okay.
It's like recognizing that a hammer and a screwdriver, while different tools share a common purpose to build or fix things.
I love that.
Yeah.
It's like we're going meta on algebra,
Mm.
looking for the universal principles that govern all these different systems.
Exactly. And this sets the stage for Obua's next big idea,
Right.
using specific terms and templates to express these abstract concepts in a formal language.
Okay. Terms and templates. Those sound familiar from computer science.
Yeah.
Is there a connection here?
Absolutely. Abstraction logic has deep ties to computer science.
Okay.
Think of a signature as the programming language you're using.
Okay.
It defines the available commands and functions, the building blocks you can use to create a program.
Okay. I'm starting to see the analogy.
Sure.
So how do terms and templates fit into this programming language?
Terms are like the specific instructions you write in your program.
Sure.
They're expressions built from variables, abstractions, are operators, and applications,
Okay.
which tell the computer how to manipulate those objects.
So if our signature included an add operation, a term might be add x, y, where x and y represent variables. Is that right?
You got it. Now,
Um,
templates take this a step further. Imagine you want to write a program that can add any two numbers, not just specific values for x and y.
Okay.
That's where templates come in.
Okay.
They introduce bound variables, which act like placeholders that can be filled with any value from your universe.
So a template is like a blueprint for a whole family of terms.
Right.
A more general and flexible way to express operations.
Precisely. And Ogua provides some really neat examples in the book using a signature he calls T.
Okay.
He shows how templates can be used to represent complex mathematical expressions within a calculator-like abstraction algebra.
This is amazing.
Yeah.
But as we get more complex, I wonder if we'll run into issues with ambiguity. For instance, do the names of those bound variables matter?
Yeah.
What if I use I instead of J in the summation?
You've hit upon a crucial challenge in formal systems, alpha equivalence.
Okay.
It means that two templates might look different because they use different names for their bound variables.
Okay.
But logically, they should mean the same thing.
Right, like that summation example. The underlying math doesn't change if we use different letters for the index variable.
Exactly.
So how do we handle this potential for confusion?
Obua has a clever solution. De Bruin indices.
Okay.
Instead of using names, we replace bound variables with numerical indices, indicating their position within the template structure.
That's brilliant. So the index 0 would always refer to the most recently bound variable
Yeah.
to the one before that, and so on.
Exactly. This eliminates any ambiguity caused by variable names.
Okay.
Two templates with different names, but the same structure will have identical De Bruin representations.
Okay. This De Bruin system is blowing my mind.
Yeah.
It seems like we're creating a language that's both incredibly precise and incredibly powerful.
Right.
But how do we actually manipulate and work with these De Bruin terms? We need a way to perform operations on them.
Absolutely. And that's where the concept of substitution comes in.
Okay.
We need to be able to replace variables with other terms just like you do in algebra when you solve for x.
Right, but I'm sensing this might get a little tricky with De Bruin terms.
Yeah.
What about those numerical indices? Could they get messed up during substitution?
You're sharp.
Oh.
There's definitely a potential problem here called free variable capture.
Okay.
Obua illustrates this with a great example in the book, showing how a naive approach to substitution can lead to unexpected and incorrect results.
Yikes. That sounds like a recipe for logical chaos. Does De Bruin help us avoid this?
That's the beauty of it. De Bruijn indices provide a robust and elegant solution to the problem of free variable capture.
Okay.
By using numerical indices instead of names, we ensure that substitutions happen correctly, respecting the scope and binding of variables.
I'm starting to see why Obua is so excited about this system. It's incredibly powerful and addresses many complexities in formal systems.
Right.
But we still need a way to assign values to these De Bruijn terms, right? How do we actually compute with them?
Excellent point. That's where evaluation comes in. Obua defines a formal process for evaluating terms within a given algebra,
Okay.
mapping variables to values and applying the defined operators based on the structure of the De Bruijn term.
So we're taking these abstract representations and turning them into concrete calculations.
Precisely. And he even proves a theorem showing that this evaluation process is consistent.
Right.
Evaluating a template with De Bruijn indices yields the same result as evaluating the original template with named variables.
That's reassuring. So our De Bruijn representation isn't just a convenient shorthand.
Right.
It's a logically sound way to represent and manipulate mathematical expressions.
Exactly. To make this even more rigorous, Obua introduces the De Bruijn abstraction algebra, denoted ADB.
Huh.
Imagine an algebra where the universe itself consists of De Bruijn terms.
Wow, that's pretty meta.
Yeah,
So now we're doing algebra with the very language we're using to describe algebra.
you got it. And using this algebra, Obua formally proves that templates differing only in the names of their bound variables. Those alpha equivalent templates we talked about
Yeah.
have the same alpha conversion. It all ties together beautifully.
This is all incredibly fascinating.
Yeah.
We've gone from a simple mathematical universe to this incredibly sophisticated system of abstraction algebra and De Bruijn terms.
Right.
And if I understand correctly, this is just the foundation for Obua's abstraction logic, right?
You're absolutely right. We've laid the groundwork.
Okay.
And now we're ready to see how Obua applies all of this to the world of logic and reasoning.
That's where we'll pick things up in part 2 of our deep dive. Thanks for sticking with us so far. We'll be back soon to explore how all of this leads to a powerful new system of logic.
Sounds good. Welcome back. I hope you're ready for more, because we're about to take this abstract journey to a whole new level
Okay.
by exploring how Obua connects this intricate system to the realm of logic.
My head's still spinning from all those De Bruijn indices and whatnot, but I'm definitely up for the challenge. Where do we start? I've got this intriguing quote from mathematician Terence Tao in my notes, something about turning math into logic.
That's a perfect jumping off point.
Oh.
Obua was inspired by Tao's suggestion that material implication,
Okay.
the idea that A implies B, could be reinterpreted as B, is at least as true as A.
Okay, that's a thought-provoking way to look at it.
Yeah.
It shifts the focus from a strict cause and effect relationship to kind of comparing the truthiness of different statements.
Exactly. And that's the key to how Obua bridges the gap between abstraction algebra and logic.
Okay.
He introduces the concept of truth values,
Okay.
which, just like the mathematical objects in our universe, can be compared and ordered.
So we're not just dealing with numbers and sets anymore.
Right.
Now we're adding truth values into the mix.
You got it. It's like expanding our mathematical toolbox to include tools for reasoning about truth and falsehood.
Okay.
And just like we needed operations to manipulate those mathematical objects, we now need a way to compare and order these truth values. That's where the logical order comes in.
So the logical order tells us how these truth values relate to each other.
Yeah.
Like which ones are more true than others.
Precisely. Think of it like a spectrum of truthiness,
Okay.
instead of just true and false.
Right.
We might have a whole range of values in between.
Okay, that's already expanding my understanding of logic.
Good.
So how does this logical order work?
It involves 3 key components.
Okay.
First, we have a set of truth values noted T.
Oh.
The set could be as simple as true, false, or something much more complex,
Right.
depending on the specific logic we're building.
I'm imagining a sliding scale of truthiness with all sorts of shades of gray between the extremes of true and false.
That's a great way to visualize it. Next, we have a partial order on these truth values denoted.
Okay.
This tells us which truth values are at least as true as others,
Okay.
but it doesn't necessarily rank every single value.
So it's not like a strict hierarchy where every truth value has a definitive place.
Yep.
Some might be incomparable.
Exactly. It's more like a web of relationships, with some truth values being above others,
Okay.
while some are simply unrelated.
Okay, that makes sense.
Uh-huh.
What's the third component of the logical order?
The third part is a function that maps any value in our universe, U, to a truth value in T.
Okay.
This allows us to assign a degree of truthiness to any mathematical object, even something as abstract as a function or a set.
So even complex mathematical expressions can have a truth value associated with them.
Yeah,
That's pretty powerful.
it is. And it circles back to that Tao quote we started with.
Yeah.
Instead of just saying this expression equals that value,
Right.
we can now say this expression is at least as true as that value.
Okay.
We're adding a whole new layer of meaning to mathematical statements.
I'm starting to see how this all comes together. But you mentioned something earlier that I wanted to circle back to.
Sure.
Complete lattices.
Yeah.
What are they,
Yeah.
and why are they important in this context?
Great question. A complete lattice is a special type of set where we can always find the greatest lower bound and the least upper bound for any collection of elements.
Okay.
Think of it like this. Imagine a family tree.
Okay.
The greatest lower bound for a group of people would be their most recent common ancestor, someone who's an ancestor to everyone in that group,
Okay.
but as low down the tree as possible.
Okay, I'm visualizing that.
Yeah.
So the least upper bound would be like the first person who's a descendant of everyone in the group, the highest point in the tree that connects them all.
Precisely. Now, in the context of truth values, the greatest lower bound corresponds to the logical operation.
Hmm.
And if we say A and B, we're essentially looking for the truth value that's at least as true as both A and B,
Okay.
but not any truer than it needs to be.
So the complete lattice guarantees that this AND operation will always have a well-defined result, even if we're dealing with complex truth values.
Exactly. And the same goes for OR, which corresponds to the least upper bound. The complete lattice ensures that these basic logical connectives have a consistent and meaningful interpretation within our system.
That makes sense. But what about more complex logical operations like implication?
Right.
How does a BUA handle that?
That's where things get even more interesting.
Okay.
Remember those distributive laws from algebra? The ones about distributing multiplication over addition and vice versa?
Vaguely.
Mm.
Can you refresh my memory?
Of course.
Okay.
They're basically rules about how operations interact. In logic, we have similar distributive laws involving and or.
Okay.
For example, the join infinite distributive law allows us to distribute a meet, like and, over an arbitrary number of joins, like or.
Okay, I'm starting to recall those algebraic nightmares now.
Yeah.
But how do these laws relate to implication?
Well, Obua shows that these distributive laws are essential for defining implication and exclusion as actual truth values within our logical system.
Okay.
In a complete lattice satisfying the join infinite distributive law, we can define implication. A implies B as a specific truth value,
Yeah.
denoted A, B.
So instead of just saying A implies B, we can actually pinpoint a truth value that represents that implication.
That's pretty cool. It is. And this truth value, A, B, is defined in terms of other truth values that meet a certain condition.
Okay.
It's like saying A implies B
Yeah.
is as true as the truest statement that when combined with A
Mhm.
is at least as true as B.
Okay, my brain's definitely doing some mental gymnastics here, but I think I'm following. You also mentioned exclusion.
Right. Exclusion is kind of like the flip side of implication.
Okay.
In a complete lattice satisfying the meet infinite distributive law,
Okay.
we can define exclusion A but not B as a specific truth value denoted A, B.
So implication and exclusion become first-class citizens in this logic.
Yeah.
We can manipulate them just like any other truth value.
Precisely. And this opens up a whole new world of expressive power.
Okay.
We can represent much more nuanced logical relationships than we could with just and, or, and not.
This is all starting to sound very powerful.
Right.
But are there any complete lattices where both distributive laws hold, allowing us to have both implication and exclusion?
That's a great question. And that's where complete bihating algebras come in.
Okay.
These are special lattices where both distributive laws hold, giving us the full expressive power of both implication and exclusion.
So these bihating algebras are like the ultimate playgrounds for logic,
Right.
where we can combine and manipulate truth values in all sorts of ways.
Exactly. And the amazing thing is that these bihating algebras aren't some rare esoteric mathematical object. They're
Okay.
surprisingly common.
Yeah.
Any complete Boolean algebra, like the one underlying classical logic, is a bihating algebra.
Okay.
And any finite distributive lattice is one too.
So we're not just talking about some theoretical curiosity.
Yeah.
This system is grounded in well-established mathematical concepts.
Precisely. With this powerful framework in place, we're finally ready to explore how Obua defines formulas, rules, and sequence in abstraction logic.
I'm eager to see how this all comes together. Let's dive into those formulas.
The fundamental idea in abstraction logic is that any term,
Oh,
remember those expressions we built from variables, abstractions, and applications back in part 1,
yeah.
can also be interpreted as a logical formula.
So we can take a mathematical expression and view it as a logical statement
Yes,
that's blurring the lines between math and logic in a fascinating way.
exactly. And to make this more concrete, Obua introduces the concept of the truth range of a template.
Truth range. What does that mean?
It's about acknowledging that a template,
Right.
with its bound variables,
Right.
can represent a range of truth values depending on the values assigned to those variables.
Okay.
So instead of having a single fixed truth value,
Right.
a template can have a whole spectrum of possibilities.
Okay, so it's like saying this expression might be true, false, or somewhere in between depending on what we plug in for the variables.
Precisely. And this allows us to define sequence, which are essentially pairs of collections of templates. Think of a sequent like an argument with premises and conclusions.
Okay.
We have a set of antecedents, the premises,
Okay.
and a set of succeedants, the conclusions.
So a sequent is like saying if these premises are true, then these conclusions follow.
Exactly. Abua also defines special types of sequence called rules and formulas.
Okay.
A rule is a sequent with a single conclusion,
Okay.
and a formula is a rule with no premises.
Okay.
Essentially just a term view as a logical statement.
So we're building up a hierarchy here. Formulas are the basic building blocks.
Right.
Rules combine them to form logical arguments.
Exactly.
And sequence generalize that to allow for multiple conclusions, like a logical construction set.
I like that analogy.
Okay.
And Obua then defines what it means for a sequent to be valid based on the logical order we've established.
So a valid sequent means that the conclusions are at least as true as the premise is right.
Yes.
Everything follows logically from what came before.
Precisely. It's all about making sure our arguments are consistent with the truth values and their relationships as defined by the logical order.
Okay.
But how do we actually demonstrate this validity? How do we prove things in this system?
Right.
That's where the concept of proof systems comes in.
Okay, I'm sensing that this is where we're going to finally see the power of this whole system come to life. Bring on those proof systems.
Absolutely. Obua describes 3 different systems: sequent calculus, natural deduction, and sequent deduction.
Okay.
Each offers its own way to construct proofs, essentially step-by-step arguments that demonstrate the validity of a sequent.
So each system has its own set of rules, its own strategy for playing this logical game.
Exactly. But before we delve into the details of how to build proofs,
Okay.
we need to take a step back and talk about models in abstraction logic.
Okay.
It's about connecting these abstract systems to concrete mathematical structures.
Models. That sounds like a whole other level of complexity. I'm ready to have my mind blown again.
A model in abstraction logic is a way to interpret the symbols and rules of our logic in a concrete setting.
Okay.
It consists of an abstraction algebra, a logical order, and a valuation space,
Okay.
which defines the allowed mappings from variables to values.
Okay.
It's about setting the boundaries for what counts as a legal interpretation of our logic.
So a model is like a specific instance of our logic, a way to ground it in a particular mathematical world.
Exactly. Abua distinguishes between standard models,
Okay.
where we consider all possible valuations,
Okay.
and non-standard models,
Sure.
which restrict the valuations in some way.
Interesting. So different models could lead to different conclusions about the validity of a sequent.
Precisely. And this brings us to the concept of soundness in a proof system.
Okay.
Soundness guarantees that if we can prove a sequent using a particular system,
Okay.
that sequent is valid in any model of the logic.
Yeah.
It means our proof system isn't leading us astray.
Right.
If we can prove something, it's actually true.
That's reassuring. It would be frustrating to build an elaborate proof only to find out it's based on faulty logic.
Absolutely. And Obua goes to great lengths to prove the soundness of each proof system he presents.
Mm-hmm.
He shows that natural deduction and sequent deduction are sound in general,
Okay.
while sequent calculus is sound for a particular type of model called a by-H model.
Okay. I'm feeling a bit overwhelmed by all the technical terms,
Yeah.
but I think I'm starting to grasp the big picture.
Good.
We've created this incredibly powerful system for representing logic. And we have ways to prove things within that system.
Mm-hmm.
And we know those proofs are actually meaningful because they're sound.
You've summarized it perfectly. And with that solid foundation in place,
Okay.
we're finally ready to dive into the specifics of how to construct proofs in abstraction logic.
That's where we'll pick things up in part 3 of our deep dive. I can't wait to see this system in action. Welcome back to our deep dive into abstraction logic. We've laid the groundwork exploring Obua's mathematical universe, delving into abstraction algebra, and even wrapping our heads around those mind-bending de Bruijn indices. Now are we finally ready to see how this all comes together in the world of proofs? I'm eager to see this system in action.
You're in for a treat. It's amazing how this complex theoretical framework leads to proof systems that are surprisingly intuitive. Let's start with the sequent calculus.
Okay, sequent calculus. Remind me, how does this system work? What's the basic idea?
Imagine you're building a logical argument brick by brick. You begin with axioms,
Yeah.
the self-evident truths of your system, the bedrock upon which everything else is built.
So they're like the givens in geometry, the statements we accept as true without needing proof.
Exactly. From these axioms, you can derive new truths using a set of inference rules.
Okay.
Think of them as logical Lego blocks that allow you to combine existing truths to create new ones.
I'm starting to see the structure here. It's like a game with clear rules for how to move from one truth to the next. What kind of inference rules do we have in sequent calculus?
There are quite a few, but they can be grouped into categories.
Okay.
We have structural rules that let you rearrange the premises and conclusions of your argument without changing its logical meaning. It's like tidying up your logical workspace, making sure everything is in the right place.
So we can add or remove premises, rearrange things, and it won't affect the validity of the argument. That's pretty handy.
Exactly. Then we have logical rules that introduce specific logical connectives like and, or, implies, and not. These rules capture the essence of how those connectives work in our logical system.
Okay, so these rules let us build up more complex arguments by combining simpler statements using the familiar logical operations. It's starting to feel like the logic we use in everyday reasoning.
That's the beauty of it.
Yeah.
And finally, we have the cut rule, one of the most powerful but also controversial rules in logic.
Cut. That sounds intriguing. What's so special about this rule?
The cut rule lets you introduce lemmas, intermediate steps in your argument.
Okay.
Imagine you want to prove statement D, but it's easier to first prove a helper statement C,
Okay.
and then use C to prove D.
Okay.
The cut rule allows you to skip the middleman and go straight from the original premises to D,
Okay.
eliminating the need to explicitly state C.
So it's like taking a shortcut in our reasoning, streamlining the argument.
Exactly. But like any shortcut, it can sometimes make things harder to follow.
Right.
The cut rule can lead to proofs that are less intuitive and harder to understand,
Yep.
and it can sometimes cause problems in the overall system.
So it's a powerful tool, but one that needs to be used carefully. Now, you mentioned two other proof systems, natural deduction and sequent deduction. How do those differ from sequent calculus?
Natural deduction is a bit more streamlined and closer to how we naturally reason.
Okay.
It focuses on proving rules, those sequence, with a single conclusion. The rules are designed to mirror the way we typically think about logical connectives.
Can you give me an example of how this works in practice?
Sure. Let's take implication. A implies B. In natural deduction, we might have a rule that says, if assuming A, we can derive B, then we can conclude A implies B.
Ah, that makes perfect sense.
Yeah.
It's like saying, if I assume this thing is true and it leads me to this other thing being true, then the implication holds. It's very intuitive.
Exactly. Natural deduction aims to capture those natural patterns of reasoning in a formal way.
Okay.
And Obua shows that this system is sound, meaning any rule we prove using natural deduction is guaranteed to be valid.
That's great to know. What about this sequent deduction system? Where does that fit in?
Sequent deduction is a sort of hybrid between sequent calculus and natural deduction.
Okay.
It retains the symmetry of sequent calculus,
Okay.
where premises and conclusions are treated equally,
Mm-hmm.
but it avoids the cut rule, making it more in line with the natural reasoning style of natural deduction.
So it's trying to get the best of both worlds, combining the strengths of each system.
Precisely. And Obiwa demonstrates that sequent deduction is also sound, providing another reliable way to reason within abstraction logic.
This is all incredibly impressive. But I have to admit, it's a lot to absorb. For our listeners who might be feeling a bit overwhelmed, what's the key takeaway here? Why should they care about abstraction logic and all its complexities?
That's a great question. I think the biggest takeaway is the sheer potential of this approach. Abstraction logic is more than just a way to prove theorems.
Right.
It's a new language for thinking about the world, a framework that unifies mathematics and logic.
It's like we're seeing the world through a new lens, one that reveals deeper connections between things we might have thought were separate.
Exactly. And this could have profound implications for fields like computer science, artificial intelligence, and even our understanding of the universe itself. Imagine being able to reason about complex systems in a more rigorous and unified way.
It's like Abua has given us a glimpse into a future where the boundaries between disciplines blur and new possibilities emerge from those intersections.
Absolutely. And the fact that Obua's work is still in progress makes it even more exciting. Who knows what other breakthroughs await us as this system continues to evolve? It's definitely something to keep an eye on.
Thank you for taking us on this incredible deep dive into the world of abstraction logic. It's been a challenging but incredibly rewarding journey. We hope you've enjoyed exploring this fascinating new system of thought with us.